Hello, everybody. In this last section of Chapter 7, we are going to talk about just some of the different groups and the common reactions that these groups undergo. So before we get started, this is going to be a listing of facts, basically. You will get more out of this if you pause at this point in time and just kind of list off, what do you already know? What do you already know about metals, about nonmetals, about metalloids? What do you already know about some of these groups inside the metals, like the alkaline metals, the alkaline earth metals? What do you already know about groups inside the nonmetals? Can you tell me something that's characteristic to the whole group? Can you tell me a reaction that the whole group is likely to undergo? So now would be a good time to pause and kind of just list out everything you know. Without further ado, let's talk about metals. So in general, of course, they're going to have the characteristics of metals. They're going to be shiny, conductive, malleable, ductile, solid. These are the properties that you've learned since elementary school, right? Most of them have a really high melting point. So these are the properties that we're going to kind of add in. So melting point is the temperature, again, just like boiling point, melting point is going to be a temperature, the temperature at which it turns from a solid into a liquid. So most metals are extremely, extremely high, like think inside a volcano high, like tens of thousands of degrees. The two exceptions to these are selenium and, oops, that's not what I meant to do. So Ce and Ga, those are the two exceptions. And actually, gallium is a pretty cool metal. It'll actually melt in your hand. It melts at like body temperature. You definitely don't want it to melt in your hand. But if you hold it inside a glass tube and your heat from your hand transfers through the glass tube, you can get it to melt, which is pretty cool. But most of them are super high melting points. And then most metals are oxidized by oxygen or acid. So think rust, right? If you leave a metal in like wet somewhere, it's going to rust, right? That's because the oxygen inside the water is going to oxidize it. And oxygen floating around in the air as a gas will do something similar. It'll just take longer because it's not quite as concentrated as the oxygen inside of, well, gases aren't as concentrated as liquids, right? Gases, the molecules are farther apart. Liquids, the molecules are closer together. So if you have a liquid sitting on a metal, it's going to have a lot more oxygens in contact with the metal than a gaseous system would be. Acids will do the same thing. So acids love to steal electrons. Same thing as oxygens. Oxygens love to steal electrons, and metals give up their electrons pretty easily. So acids will also oxidize or steal electrons from metals. Okay, so when you're dealing with the metals, you get into the ions, right? The vast majority of ions are metallic ions. They're cations. All of the transition ions come from metals. So this would be a good point, a good time to remind yourself, like, yep, I need to know those. Let's go back to that list, see if I still have them memorized, see if I can apply them to these reactions where metals combine with oxygen or metals combine with acids, and they come out in the end with an ionic compound that is built from ions. So you got to know them, you got to know their charges, you got to know their names. It would be a great thing to go back and review those today or tomorrow or maybe Sunday. Okay, so here are a couple common reactions with metals. So if you combine a metal and a nonmetal, you're going to get an ionic solid. Notice here it's not quite as forthcoming as the reactions in chemistry. A lot of times the reactions in chemistry, we would list the metallic ion and we would list the nonmetallic ion. And then, of course, you would combine them into an ionic solid. right? All right, but the reactions that you're going to see on the AP test, they're not going to be quite that obvious. And so you're going to have to recognize, all right, I'm combining a metal here with a nonmetal. What's the most likely outcome? The most likely outcome is going to be an ionic solid. When you mix a metal oxide in water, what you're going to get out is a metal hydroxide. And this is one of the things about like the alkali metals and the alkaline earth metals. Alkaline means basic. And the reason they named them alkali and alkaline earth metals was because oftentimes when these metals were in the mix, what would come out would be a base. And so we'll talk a little bit more about acids and bases in the next unit that we do with chapter 4. But anything with a hydroxide attached to it, let's see if I can get my pen here. Anything with a hydroxide, which is the OH group attached to it, is probably most likely to be basic. And so when you combine a metal oxide and water, what you're going to get out is a metal hydroxide, which is basic. So again, it's not very obvious that this will happen when you're looking at the actual reactants. So again, you're going to have to recognize them as a metal oxide combining with water and know what that comes out to be. And so when you're writing this reaction, you just have to write the metal oxide. So our metal here is sodium, Na. Sodium is going to be an Na plus. Hydroxide's an OH minus. And so when they combine, they're going to combine in a 1-to-1 ratio, and you're going to get NaOH. And you should be able to balance this if we have, let's say, 2 sodiums, and we have... Okay, so we have 2 sodiums, we have 2 hydrogens, we have 2 oxygens, and it's balanced. There we go. So you don't have to evaluate. The reactants are not easily evaluated. You have to actually recognize them as a metal oxide in water. In a similar way, if you have a metal oxide and an acid, this is going to turn into a base combining with an acid. And when you have a base combining with an acid, you always get a neutralization reaction happening where the base and the acid combine and kind of switch ions around, restructure, and then they come out neutralized, which means you have mostly water with some salt or salt ions floating around. Again, in Unit 3, when we talk about Chapter 4, we will talk more about neutralization reactions, but that's the gist of it. So basically, you're going to get out a salt, which is an ionic compound, in water. So the salt is going to be made from the metal and the nonmetal. Again, you have to balance it. So since magnesium is a 2+ and chlorine is a minus, you're going to come out with MgCl2. And then the O and the H are going to combine into water. And then again, you should be able to balance it and be good to go. So there's 2 on this page that we haven't done. Let's see if you can come up with what the metal hydroxide is on one and what the salt is on the other. Okay, moving on to nonmetals. So nonmetals are the not group. They are not shiny, not conductive, not malleable, not ductile, etc. Nonmetals have this huge variety in structures that they can come out to be. Metals are pretty consistent. Nonmetals have a huge variety. And when we talk about bonding and certain types of bonding, you'll start to see why. It kind of depends on the lattice that the nonmetal forms. And so you get this huge variety. You can come out with something. Some things in nonmetals turn out to be extremely hard, like diamonds. Some things, like sulfur, turn out to be soft. You can crush it and it just crumbles inside your hands. Melting point tends to be lower. In the nonmetals, we also have a lot of gases. Think of, the halogen group. The two are gases, one's a liquid, one's a solid. Almost everything next to the halogens, oxygen, nitrogen, a lot of those come out to be gases as well. So the nonmetals contain all the gases on the periodic table. The solids and the liquids that they do contain, like the liquid of bromine, the solid of iodine, they're extremely volatile. So volatile means it turns into a gas really easily. So iodine, you actually have to keep in a very sealed container. Otherwise, the solid iodine will turn into a gas, and that gas will escape out into your chemical closet, probably. Hopefully, that's where you're keeping your chemicals, which is not something you want to occur. And so even the things that are solids and liquids, they tend to have lower melting points. And that's true for a lot of things, except these special structures that form, special lattices that form within the nonmetal group, like diamond, that turn out to be extremely, extremely hard. One of the hardest things that we know of on Earth presently. So again, we see this variety in melting points. There's a lot of diatomic elements in the nonmetals. When you're talking about metals, all your elements are going to be monatomic, right? When they appear as elements, if you have them in their elemental form, there's just one atom, like copper, Cu, or magnesium, Mg. Right? When you have nonmetals, some of them turn out to be monatomic. Some of them turn out to be diatomic. And we have those 7 famous diatomic. So if you find hydrogen in its elemental form, it's not going to be hydrogen H. It's going to be hydrogen H2. It's the molecule of hydrogen. That is the elemental form. And there's 7 of those. And remember that if you're not counting hydrogen, they make the 7 on the periodic table. We also have a couple like sulfur here. Sulfur's most common form is S8. We have phosphorus. Phosphorus's most common form is P4. But those two, the College Board won't actually hold you to. They will be impressed if you use S8 or P4, but they will also allow you just to write sulfur as S and phosphorus as P. The diatomics, they are not flexible on. You must write the diatomic elements as H2, N2, F2, things like that. All right, so just like metals have common reactions, nonmetals do also. Again, we see this same one here with the metal and the nonmetal turning into a salt. Make sure you balance the salt. Consider the charges that form. Al will form a 3+, Br will form a 1-. You have to consider those charges when you balance them. And then acids have really similar reactions to these metals. Again, we're going to see a non-metal oxide in water and a non-metal oxide in base. So a non-metal oxide in water is going to form an acid. Remember, the non-metal or the metal oxide in water formed a base. Non-metal oxides in water form an acid. And so when you are forming these, again, it's a little bit of guesswork. So you have to look at the things that you have, and you have to what I would do is just write the most common acid that forms from this. So with carbon, for example, the most common acid that forms from carbon is probably the carbonic acid, right? So if I can write carbonic acid, I'm probably going to be pretty close to the ballpark of what gets formed here. So try that down here. What is the most common acid that's formed with your nonmetal here? If you need more time, now would be a good time to pause it. And if you don't need more time, hopefully what you said was phosphoric acid, right? H3PO4. Now I know there's a couple different forms here of these acids, like is it carbonic acid or is it carbonous acid? Just take your best guess. And a lot of times with these, they'll accept more than one acid if they're common enough. So just write the most common acid, which is probably the acid that you are familiar with. If we have worked with one, that's the most common acid. And you're probably going to be in the ballpark. With the nonmetal oxides and the base, again, this functions as if you have your acid plus a base. So again, it's going to be a neutralization reaction where you end up with your salt and then your water. So again, you just want to evaluate nonmetal is going to combine with your metal, and then you're going to have water left over. Ooh, sodium and carbon, that one's not very pretty. I'm going to guess it's Na4C. Doesn't look like a very pretty salt. You could also possibly, since this is not going to be a very common compound, carbon doesn't usually form salts. Carbon usually doesn't form ions, right? And so any compound with carbon is probably going to be organic, or it's going to use one of its polyatomic form of ions. So more likely than Na4C would be sodium combining with an oxy ion of carbon, which would probably be carbonate. So Na2CO3 is probably going to be more likely. Again, some of this is a little bit of guesswork. Reactions are notoriously difficult to predict. They have even tried to build like computer models that predict reactions of new things together, and it's just extremely hard to do. And so a lot of times what we know about the reaction is what we have observed. And that's the case for you guys too. So we're going to deal with a lot of reactions in like a lab scenario. And a lot of the reactions they ask you about on the test are actually going to come from labs that we have done. So hopefully you have some familiarity with them. But if you don't, then kind of going through the process that you just saw me go through is the best way. So again, down on this one, you can think of your metal and your nonmetal forming. So if K formed with S, what would it form? If K formed with an oxy ion version of S, what would that form? And those are probably pretty likely products for you. Okay, metalloids. So metalloids are this super weird group. It kind of is the group of black sheep, right? It's the things that don't necessarily fit into metals and nonmetals together. And they don't fit very inconsistently. So for example, we have silicon here. It looks like a metal. It's pretty shiny, right? But it's also brittle. So it has this has properties of a metal. It also has properties of a nonmetal. If you look at a different metalloid, however, they are not going to have the same properties of both. Maybe another nonmetal would look like a nonmetal, but act like a metal. So the nonmetals have really inconsistent properties, and they kind of have a mishmash of properties of metals and nonmetals. Again, these are going to be super hard to predict. You're really only going to know about them if you have studied them or worked with them. And so I'm not going to expect you to know more than that, other than that, the fact that they don't like fit nicely in any of the categories until we talk about specific ones in class. Okay, so now we're going to get into a couple of the groups of metals and a couple of the groups of nonmetals just to kind of hit a couple of things. So the big groups of metals are going to be alkali metals and alkaline earth metals. Alkali metals, they are really soft. These were the ones we dealt with in chemistry last year, where we cut a piece off with a butter knife, and then we took them out of the oil, remember? And then we dropped them into water and watched them like spark and pop and stuff like that. Those were alkali metals. We did that with lithium and we did that with sodium. So they tend to be fairly soft metals. I cut it with a butter knife with a little difficulty, but still cut it with a butter knife. They tend to be very silvery, very lustrous. They're super conductive, both for like thermal conductivity and electrical conductivity. The term alkali comes from the word ashes. So the earliest isolation of some of these was from wood ashes, which is why they got that name. They are the most abundant elements in Earth's crust, seawater, and biosystems. Good for them, kind of cool. They have extremely low densities and fairly low melting points for the metals. This would be like a general reaction that you might see since they all form that 1+ ion. They're all going to, when they ionize, one electron is going to form off to leave them with a 1+ charge. They are the most active metals on the entirety of the periodic table. So a lot of times you don't find them as elements, you find them inside compounds because they're so active. Okay. So common reactions of alkali metals are just going to be reflecting that 1+ charge. If it reacts with hydrogen. Oh, that one's a tricky one. Let's do that next. If it were to react with sulfur, sulfur has a 2- charge, so you'd get something like M2S. If it reacts with chlorine, chlorine has a 1- charge, so you'd get something like MCl. Now, hydrogen is interesting here because hydrogen usually forms an H+ charge, right? But if you have an M+, you can't combine it with another thing that's positive. And so with the alkali metals, hydrogen is actually going to form an H- ion. It's extremely unusual for hydrogen to do. And the alkali metals and the alkaline earth metals are actually one of the only groups. They are the only two groups that hydrogen will actually be forced into this alternative role. When hydrogen forms the H- ion, we call it a hydride. And so what you'll see, since it's a 1+ and a 1- is an MH. So like LiH would be lithium hydride, NaH would be sodium hydride. So this is one of the interesting things that alkali metals does, is it forces hydrogen into this alternative role. When you combine an alkali metal with water, what you're going to find is that they act just like the other metals and they form a metal hydroxide. But when they form this metal hydroxide, they also form hydrogen gas. And so this is what we did in the demo with lithium and sodium in chemistry. We took lithium, we dropped it into water, we watched it kind of bubble. That was the hydrogen gas. We watched it spark because it releases so much of this bonding energy at the same time. And then what we were left with was a very basic solution in our little water glass because we had our metal hydrate there. It's extremely vigorous. The energy is all released at the same time. And it's so vigorous that sometimes that energy that's being released from those bonds being broken and reformed will actually light the hydrogen gas on fire. So if you were in one of the classrooms where you saw the flame that formed on like a bubble and the flame kind of traveled around, or if you heard a pop, that was because this very exothermic energy that was being released, very vigorous, actually lit the hydrogen gas on fire. Okay, alkali metals, here are some examples. They can react with oxygen to form oxides. So an oxide is your normally predicted ion of oxygen. As you go down the family, though, the ion of oxygen that gets formed gets stranger and stranger and stranger. So lithium on the top will form a very normal oxide with oxygen, like LiO2, right? Sodium will actually form a peroxide ion. So you won't get Na. Oh, that's not right. Lithium with an oxide would be Li2O. That would be your oxide with lithium. With a peroxide, you would get sodium reacting with the peroxide ion. Notice that this is the oxide ion and this is the peroxide ion because it comes with the subscript. So you'd get Na2O2, which would be your formula. We're used to dealing with hydrogen peroxide, which is just H plus combining with this peroxide ion. So you get H2O2. That's hydrogen peroxide. You can also get sodium peroxide. When you combine potassium, rubidium, or cesium with oxygen, you actually form a superoxide ion, which is extremely rare and unstable. Here is your superoxide ion. And so this would be an example because K has a 1 plus and the superoxide ion has a 1 minus. You would form KO2. Again, metallic alkali metals are so reactive that sometimes they force things into unusual circumstances, and you saw that with hydrogen. This is a good example with oxygen. Okay, colors of alkali metals. Salts of alkali metals are going to be colorless unless they're with a colored anion. Remember that electron, so if we look at lithium, right? Lithium has 2 core electrons and then 1 alkali or 1 valence electron. And when it forms Li plus, this valence electron is taken away. And so you don't have that valence electron anymore to excite into higher energy levels and fall back down. And these core electrons, they can do it, but it takes so much more energy for them to get pulled out of that core shell that they're not going to tend to do it. And that's why they're typically colorless. Alkali metals in a flame, however, have very characteristic colors because a lot of times when we're putting alkali metals in a flame, we'll put alkali metals themselves into water, and the flame that comes out of that may have a characteristic color. You'll also, when we put alkali metals into the flame, like in the flame test lab, we didn't put the alkali metal itself in there. We put a salt of the alkali metals in there. So like we use lithium chlorine, And now we have extra electrons that we can kind of bounce around to give us those characteristic colors. Sometimes on the test, you'll see the test ask, like, what color comes out of putting lithium chlorine in a flame? And again, it comes down to kind of familiarity with that stuff. Is it worth your time to go memorize it for one question that may or may not show up on the test? Probably not. But as you deal with kind of flame tests more, or these kind of experiences more, you'll get more familiar with it and you'll start to recognize some of the colors that come out of it. Sodium's a really common one. Sodium has like a yellowish orange flame. Potassium is super red. Potassium's another one they ask you about. And then lithium tends to be like this purple. Oh, and copper is like that Harry Potter blue, or like a greenish blue. I would say those four are probably the most common that they might ask you about. So if you're going to go memorize them, memorize those four. Otherwise, it's probably not worth your time to go memorize the colors of the flame. Okay, alkaline earth metals. They're all solids. They have very typical metallic properties, more typical than the alkali metals will have. They're harder, like a typical metal would be. They're more dense. They have a higher melting point. So all of these characteristics are very much more typical metallic properties. The first ionization energy is not quite as low as the first ionization energy for an alkali metal. And if we look at two of these, like lithium and beryllium, for example, we can see why, right? Beryllium is going to have 4 plus nuclear charge. Lithium is going to have a 3 plus nuclear charge. So the Z effective on beryllium, 4 minus your 2 core is 2. The Z effective on lithium, 3 minus your 2 core electrons, 1. The Z effective on beryllium is going to be higher, and so it's going to take more energy to remove that electron and ionize beryllium, right? So that would be why your I1, your first ionization energy is not quite so low. And it implies that it's not quite as reactive as the alkali metals. And so we can see this when we're comparing the alkali metals to water. Beryllium won't react with water under any circumstances. Magnesium won't react with water unless it's steam. So unless that water has that like super high kinetic energy and the water particles are actually moving extremely fast, that gives you that initial impact with magnesium that can be enough to start the reaction. Calcium will actually react with water, but it's a slow reaction. It's not vigorous like what we saw with like lithium or sodium. Common reactions that you should know with this one, of course, if you combine them with a nonmetal, it's going to form a salt. The M2 in this example, however, or the M in this example is going to form, it's going to let go of 2 electrons and it'll form an M2 plus charge. So that's different from the alkali metals, right? Which we would predict from the families. They have a relatively high reactivity compared to the other metals on the periodic table, but not compared to the alkali metals. Again, you're usually not going to find alkaline earth metals as elements in the crust because they are relatively reactive. Again, you're going to find them in compounds, in salts, right? I2 ions have a noble gas configuration, just like the lithium ions. So what color should they be? Colorless, right? Unless you combine them into a salt, and then they'll give out these characteristic colors, just like alkali metals. Okay, so now we get into a couple of groups of the nonmetals, like hydrogen. Hydrogen, it's a nonmetal, it's colorless, it's diatomic. All of that should be review. When they form with other things, like when they combine with other nonmetals, they can form a variety of different compounds. Hydrochloric acid, for example, is a solid. H2O is a liquid. So they can form this variety of compounds. It has an unusually high ionization energy because that valence electron has no shielding between the nucleus and the valence electron. So there's no shielding. It's extremely close to the nucleus. And so that ionization energy is going to be super high trying to pull that electron away. You really won't see that electron pulled away unless it's stabilized by something. When it does form molecules, it's going to be very exothermic. So you'll see this huge release of energy, just like with the alkali metals. And then the only time we really see it forming a hydride is with those active metals like we just talked about. The oxygen group. The oxygen group, as you move down the group, it becomes more metallic. Oxygen is a gas, but everything else in its group is a solid. The top three are considered to be nonmetals. One is a metalloid, and then polonium at the bottom is a metal. The metal polonium is really interesting. It's super radioactive. It's also pretty rare, but it's in the oxygen group, and so it has some reactivities that line up with oxygen, which is kind of interesting. Oxygen has multiple allotropes. Allotropes are different molecules that form with the same element. So the one that we're the most familiar with is the common one, which would be elemental oxygen, O2. It also forms O3, which we know of as ozone. Oxygen can be turned into ozone. It is has an enthalpy or a heat of reaction of 284 kilojoules, which is fairly large. It's also positive, which means that energy has to enter the system in order for this to happen. And so we see ozone created when there are huge deposits of energy, like in lightning strikes would be a good example. Oxygen has a tendency to attract electrons. Again, it's a fairly small molecule. It just has two energy levels, so those valence electrons are fairly close to the nucleus, shielded by just two electrons. So it actually has a very, very, very high tendency to steal electrons from other groups. There are three ions, the oxide ion, the peroxide ion, and the superoxide ion, which we talked about when we talked about the alkali metals. The most common form we see by far is the oxide. Peroxides and superoxides will actually react with themselves, and then they will almost like a decomposition reaction, and they'll kind of like, what's the term I'm looking for? They'll decompose into much more stable things like water and oxygen. And so if you look at like a peroxide bottle, for example, it has a very special cap and it's brown. So the decomposition of hydrogen peroxide is catalyzed by sunlight, which is why the bottle is brown. And then it has this special cap that's designed to release gas, because this will happen inside the bottle on your shelf in your laundry room, right? Or wherever you keep your hydrogen peroxide. And so it'll slowly decompose into oxygen gas. And if the cap doesn't allow the oxygen gas to escape, the whole bottle is going to explode. So they design these caps to allow this gas to escape. If you buy super high concentrated peroxide, it actually comes in this little bottle that looks like an accordion, and you have to store it. You have to agree to store it in like a bomb-proof refrigerator or something crazy like that. It's kind of exciting. All right, the sulfur family. So sulfur also has several allotropes. S8 is the most common, and like we talked about, you can write it as S8. You can also write it as S. The S8 form is yellow and has this very distinct smell to it. If you've ever gone to Yellowstone or driven by a sulfur pit, you will definitely know what that smell is. It has a tendency to gain electrons from other elements to form sulfide. It's a very common reaction. It's really common with metal sulfide. So when you combine it with a metal, it's going to form your predicted ionic compound or your predicted salt. Sulfur and its compounds, which are found in coal and petroleum, are burned in oxygen. This is one of the, if you take like environmental science, you'll talk about sulfur a lot, because this is one of the biggest concerns with thermal power plants or coal burning power plants, because sulfur dioxide gets released into the atmosphere and then it forms acid rain, right? So sulfur dioxide can react with water, and the acid is formed, just like we talked about, right? A non-metal oxide with water is going to form an acid. A non-metal form a non-metal oxide acid. And so it's going to form sulfuric acid. And that is actually what is in rain that is dissolving statues and stuff like that today. And that's not great. So we want to find energy sources other than coal burning plants, right? Okay, halogens. You're probably pretty familiar with a lot of the characteristics of halogens. They are salt formers, so they're going to be really active, right? They are the non-metal equivalent of the alkali metals, highly reactive, form salt very quickly. You either are going to find them floating around in their diatomic elemental state, or you're going to find them in salts, because they are stabilized by that reaction into your ionic compound. They're all very typical nonmetals. Melting point and boiling point will increase as atomic number increases as well. And so you find the top ones to be gas. And then as that melting point and boiling point increases, the bottom ones you're going to find as liquids and solids. That would be like fluorine, chlorine. The liquid would be bromine. The solid would be iodine. They are all diatomic, and they all have characteristic colors too. So fluorine tends to be pale yellow. Chlorine is like a yellow green. Bromine's going to be a reddish brown. Iodine's going to be like a grayish black. And the vapor that comes off is actually purplish, which is kind of cool. They have a highly negative electron affinity, so they are extremely electronegative. They have a high electronegativity, and they tend to gain electrons from other elements in that reaction. X is a very common variable to use for halogens, just like M would be a common variable to use for metals. X is going to be used for halogens, capital X. Some specific examples of halogens. Fluorine is really common. You can see here a reaction with fluorine and a metal into a very typical salt. Fluorine with water is going to form an acid and oxygen. Fluorine with a non-metal oxide is going to form your covalent compound here and oxygen. All of these reactions, because they're dealing with fluorine, are going to be highly exothermic. So they're going to give off this huge burst of energy, either in heat or light. Fluorine's really difficult to deal with and also very dangerous. And so the industries tend to try to avoid using fluorine. They try to find alternatives to using fluorine. And if they don't, they have to be really careful about how that fluorine is stored. As far as these reactions go, I wouldn't spend time memorizing these ones for fluorine. It's good to kind of see. You can always reference them back. We will not be dealing with fluorine in the lab. And so fluorine tends to come up in ionic compound situations a lot on the test, but not necessarily other situations because it's not as common of an element to use. Chlorine is used in a lot of different industries. Chlorine used to be stored in tanks at our wastewater treatment plant. But again, because chlorine is pretty exothermic when it reacts and it's pretty reactive and not super stable, industries try to move away from storing tanks of chlorine on their land. And so our wastewater treatment actually went from using chlorine as kind of a last ditch sanitizer for the water that they send out into the river. And they moved to using ultraviolet radiation, which is pretty cool. Also, we get less chlorine in our river that way, which is great. It is used in a lot of industries, though. A lot of pools actually store tanks of chlorine in their back room. Some pools use chlorine tablets, so you'll drop in like a salt of chlorine into the pool and that'll sanitize it. But if you have like a bigger pool system, a lot of those bigger pool systems will use chlorine tanks of chlorine gas. Chlorine is produced by electrolysis of brine, actually. And so you take this salt solution, which is the brine, and you run electricity through it, and the electricity actually splits it up and causes the reaction to occur. And this is what you get out of it. Oftentimes, chlorine is the targeted product there. It reacts slowly with water. It does react slowly with water. And when it reacts with water, just like any other metal or non-metal oxide reacting with water, it's going to form an acid. So HCl is a common acid that it might form. HOCl, which is the hypochlorite ion, so hypochlorous acid, this is what you're going to find in pools. This is what the chlorine is that people refer to in pools. Oh, and I should say, because the hypochlorous acid is so reactive, it's not a very stable ion. When it comes into contact with organic compounds, it's going to react quickly with those organic compounds. And that's why it's a disinfectant, because when it comes in contact with bacteria, it's going to react. And with that bacteria, destroying both things, actually. Same thing when it comes in contact with like the protein coat of a virus, it's going to react with that, disabling the virus and neutralizing the hypochlorous acid. Same thing with your skin or your hair. This is why your skin gets itchy when you get out of a pool, because the hypochlorous acid has actually reacted with the organic tissue that is your skin and broken that down a little bit. And so now your skin is going to have that layer that kind of peels away, and it's going to grow new skin underneath. Or the pigment in your hair, if you swim in pools long enough, is like stripped from your hair because that pigment reacts. That pigment protein reacts with the hypochlorous acid. It's kind of a fun thing to think about as a swimmer. All right. Oops. Halogens in general, here is a general reaction with halogens with hydrogen. That would be a good reaction to know. Notice they both start diatomic and then they're going to form their balanced salt. Those coefficients don't, or the subscripts don't get carried along with the reaction. You have to rethink H plus X minus balances into HX. They're extremely soluble salts. They're extremely soluble in water. Extremely soluble elements also, and they're going to dissolve to form hydrohalic acids. So hydro is going to have an H. Halic is referring back to halogen, so that's the HX. So any of them, HF, HCl, HBr, HI, we call those hydrohalic acids. And then next chapter in Unit 2, so Chapter 4, we'll talk about acids. We'll talk about weak and strong acids. All right, noble gases, last group here. They are nonmetals. They are all gases at STP, standard temperature and pressure. They are all monatomic. They have filled s and p orbitals, so they get this super stable, extremely large ionization energy. They're known as inert, which means they are non-reactive. Some of them can be forced into compounds. Here are a couple examples. Xenon and krypton, some of the bigger noble gases, have been forced into compounds. Again, once we get to bonding, we'll talk about how this happens and why it happens with big rather than small elements. And then the smaller ones like hydrogen and neon, they have not been forced to form compounds. They are extremely stubborn in their inert characteristics. So yeah, noble gases, pretty standard, very consistent. And that's it. That's the whole chapter 7 for you. So let me know if you have questions, and I'll see you next class.